Hi, I'm Alexander, so I'll tell you a little bit about my rotating rings kinetic sculpture here. So here we have two rings, a red one and a blue one. And as you can see, there's something different between the two. If you look at the top of the rings, the red one is rotating smoothly, whereas the blue one is jerky. So why is that? What's the difference? Well, if we look carefully, here's what the difference is. On this one, the orientation changes. So you have two pivots here on the two red rings, and you have a single beam between them on the same side. Whereas if you look here, there's a 90-degree twist. You have a pivot here, but then you have a 90-degree angle before you have the next pivot. So why does that make a difference? Well, each of these is in effect a universal joint, like you would find in a truck or any vehicle. So a universal joint lets you transmit rotation around a corner. But a universal joint is not constant velocity. So what that means is even if the input turns at a constant speed, like here, the output of the universal joint is not quite turning at a constant speed. It's accelerating and decelerating constantly as it rotates, and you can't tell really that this is not a constant speed, but it's not. Now in the red ring, because of the orientation of the joints, that non-linearity, that non-constant speed, cancels out. When we get to the second one, that is going at a constant speed again, and then this is not quite constant speed, and then this is. So they cancel each other out as you go around the ring. Whereas the blue one, because they're oriented differently, the non-linearity adds up. So this is not quite constant speed, this is a little more jerky, this is a little more jerky still, until you get to the top. So that's the difference. And then I could also tell you about the one there, which kind of forms part of the same story.
Sure, yeah.
So over here, this is a remarkable design for a constant velocity joint. So again, the rotation goes round a corner. You can transmit power through an angle, but it is constant velocity. So if you turn the input at a constant speed, then the output is turning exactly at a constant speed. And there's a few designs for constant velocity joints, but there are not many that work just using pivots. A lot of them have sliding surfaces. So this one was invented by a company that calls itself Patacon, I believe, and it's called the Pat-Dan coupling. This company has a website with lots of very, very interesting inventions, and this is one of them. And I didn't really understand how it worked, so I thought I would try to make it out of Lego. And there it is. The proper one, if it was made from machine parts, would be able to turn through a much bigger angle, but this one only turns through a few degrees.
Yeah, those are incredible, and I love how you kind of use some real-world inspiration for that machine.
Oh, yeah, definitely. It's a really interesting invention.
What inspires you, and what do you find so interesting about the Technic creations, and what kind of drives you to keep making more of these types of builds?
A lot of it is ideas stolen from here and there. I mean, I look at the internet, I look at kinetic sculptures, I look at just interesting videos I find online, and I think, okay, maybe I could do that in Lego, or maybe I could do something a little bit different in Lego, or maybe I just want to understand how it works, so I try to make it in Lego.
Right. Well, that's fascinating. I appreciate you showing those builds to us. Thank you.